I'm Ganesh Duraisamy from Anna University, Chennai, Tamil Nadu. I'm going to present my talk on methanol dimethylether dual fuel RCCI combustion engine. It is part of the DST project I'm going to share with you all. As Professor Avinash rightly said in the yesterday discussion, that ICE engine is not the problem is with the fossil fuel. So we have to select the right combination of fuel for the engine applications to make it fuel efficient as well as to cut down the carbon footprint from the internal combustion engines. So this particular work is in line with that aspect, that is by adapting low carbon fuels for an engine application, and we can make the system fuel efficient and as well as free from the carbon dioxide. So here we worked on a low temperature combustion strategy, and we all of us know that low temperature combustion strategy is very attractive in terms of thermal efficiency and as well as its NOx and soot reduction potentials, because it is eliminates the dependency of after treatment systems with mild after treatment, and it is possible to tackle the NOx and soot emissions. Also we can get very high thermal efficiency. Generally, the low temperature combustion engines are providing more thermal efficiency by reducing the heat transfer losses and as well as minimizing the energy loss through the engine exhaust gas compared to the irreversibility losses that is associated with the combustion process. So if you want to gain more thermal efficiency from the low temperature combustion engines, and we have to reduce the combustion duration and as well as we have to get the appropriate combustion phasing. These two are very, very important. So to get high thermal efficiency along with proper combustion phasing control, and RCCI is one of the potential low temperature combustion strategy which provides better combustion control with the reduced combustion duration. Basically, it is a dual fuel combustion technology which uses two different reactivity fuels, namely the high octane and high cetane fuels, because these two are having two different auto ignition characteristics. And by using this, and that is this particular approach uses the in-cylinder blending approach. By using the in-cylinder blending technique, we can alter the in-cylinder reactivity gradient, because many studies on low temperature combustion and confirmed that LTC engine requires high reactivity at the lower loads and low reactivity at the higher loads. So this clearly indicates that we need the continuous change in the reactivity with respect to engine load and speed operations. So that is possible by using the in-cylinder approach. In RCCI, the high octane fuel, which is called as the low reactivity fuel, is supplied in the intake system of the engine, so that because of its high volatility in nature, it premixes with the air and forms a very good premixed air fuel mixture, which is injected and then compressed, and then for igniting it, and the high reactivity fuel is injected normally in multiple pulses. In most of the studies, the high reactivity fuels are injected in double pulses. Mainly the first pulse targets the squish conditioning, because the low reactivity fuel cannot undergo auto ignition on its own. It needs the ignition source. So we need to provide the ignition source distribution throughout the cylinder properly, and for that purpose this high reactivity fuel, that is the first injection of the high reactivity fuel, is targeted, which is called as the squish conditioning. And when you inject the fuel during this particular timing, so it ensures the distribution of the high reactivity fuel in the outer part of the cylinder, and subsequently the second injection will act as the ignition source, so it takes care of the inner part of the cylinder, so that when the ignition starts and we have the source completely available throughout the cylinder, so that the complete burning of the pre-mixed low reactivity fuel and the high reactivity fuel is possible with a reduced combustion duration, so that we can get better thermal efficiency as well as simultaneous reduction in NOx and soot emissions. So we can see here very clearly the low reactivity fuel which is injected during the intake process, and then followed by we have the injection of high reactivity fuel, and then the second injection of the high reactivity fuel, and then combustion takes place like this. So this approach provides a varied reactivity stratification as well as the equivalence ratio stratification and as well as the temperature stratification to get the controlled rate of pressure rise along with very good combustion phasings. So it is the main advantage of the dual fuel RCCI combustion technology. So when we compare this RCCI with the other LTC technology, that is HCCI and PCCI, the main advantage compared to the single fuel LTC is we can get very good combustion phase control and high thermal efficiency and CO2 reduction. But the challenges is pertaining to extending the operating range at the high load side and as well as high unburned emissions at the lower loads. The main problem at the lower load is the poor thermodynamic condition that exists when the engine starts or at the lower load conditions, and also the reactivity of the fuel, which is not supporting the oxidation properly, so that we are ending up with the very high unburned emissions in the case of RCCI, and these were the main challenge that is existing with the RCCI. So how to tackle this? And one more advantage that we get when compared to the single fuel LTC is the CO2 reduction. We can get further more CO2 reduction by adapting the low carbon fuel. So that is the main aim of this work, to choose the methanol and dimethylether as a fuel for this particular study. So in RCCI, the combustion is generally takes place in 3 stages. You can see that this graph. The first the stage of ignition is called as the cool flame, in which the pre-mixed diesel air mixture provides the start of the ignition, and then the already pre-mixed low reactivity fuel air mixture undergoes ignition, then finally the remaining low reactivity fuel also undergoes the ignition. The magnitude of this stages of ignition is completely depends on the type of fuel that we use and etc. So to tackle the issues pertaining to the RCCI engines, that is extending the high load operating range and as well as solving the unburned emissions, so we chosen methanol and dimethylether, as Professor Avinash sir pointed out in his presentation. That is, methanol is a good candidate for spark ignition engine and DME is good candidate for the compression ignition engines. So here we are combining those 2 features and using it under the LTC strategy to get the benefits out of it. So in this project, the industrial partner is the Ashok Leyland. So we received the commercial light duty automotive diesel engine, which is a 1.5 liter capacity and 3-cylinder turbocharged common rail engine, which we have modified to work with methanol and dimethylether. So why methanol and dimethylether? Because it is very simple and similar molecular structure fuel, because the molecular structure plays a very vital role in attaining the fuel reactivity stratifications. If we take the dimethylether as a better spray characteristics compared to diesel, normally the spray is wider and shorter, and it has a better automation characteristics, so that the mixing will be better compared to diesel as a high reactivity fuel. So choosing the simple and similar molecular structure fuels predominantly helps in creating the better reactivity inside the cylinder. And then another attractive thing is the low carbon content fuel. We can see here the carbon content is only 52% in the case of DME when compared to diesel, where diesel is around 86%. Similarly for methanol, we have a carbon content of around 85 to 88%, whereas with the carbon content is about 37.5%, whereas in case of gasoline it is about 85 to 88%. And there is no direct carbon to carbon bonding exists between these two fuels that ensures soot-free combustion. And then high octane, because methanol is having a very high octane number compared to gasoline, and DME is having very high cetane number compared to diesel. So this really helps in getting the very higher global reactivity gradient, which is generally measured with the parameter called Duel fuel cetane number. And then both are oxygenated fuels. So we got suggestions from various experts, those are working in DME, mainly to tackle the challenges pertaining to DME handling. So at that time, so since we don't have any clue about DME, how to use it, and all these professors across the world supported us in giving information to develop a dimethylether fuel supply system. So this is the developed engine test rig, and the Ashok Leyland, the commercial light duty diesel engine is coupled with the engine dynamometer, and then built this complete setup. And we used the NERA, the Sweden-based open electronic control unit, to control the injection of methanol and as well as the dimethylether. And we used the existing common rail system that is coming up with the engine for the direct injection of dimethylether, and we have integrated a methanol port fuel injection system by modifying the intake manifold of this engine, so that we are able to supply methanol in the intake system and DME directly into the cylinder in the liquid form. So these are some of the modifications that we carried out to provide methanol injections and as well as for the DME. And also we used various sensors. So this shows the modification done on the intake manifold to mount the methanol compatible injector, and the methanol fuel lines. What we have used is the low carbon steel based, and it is coated with ethyl vinyl alcohol to take care of the methanol corrosive issues. So Cooper Standard is a firm. They are involved in manufacturing the fuel line materials, and they supported us in manufacturing the fuel line material for methanol, and we received the fuel line material, which is basically made up of low carbon steel coated with ethyl vinyl alcohol, so to take care of the methanol issue. And we used the Bosch alcohol compatible port fuel injector, which is saturated and high impedance type, to supply methanol in the intake port. So the challenges lies with, since we committed for performing liquid direct injection of dimethylether using the existing common rail system, developing the fuel supply system is a challenge with respect to our side. And this is the system that we have developed, and you can see the dimethylether cylinder. From the dimethylether cylinder, because if you want to maintain DME in liquid form, we have to maintain the line pressure above 6 bar, because it has a very high vapor pressure and low boiling point. So we have to be very careful to avoid the vapor lock issues. Otherwise, because of the phase change issues, at any time, at any point, it can create a vapor lock issue and flow can be interrupted. So to tackle that, and based on the suggestions received from the various experts, and we built this DME system, and we used, since DME is very poor in lubricity and viscosity, and we used the recommended lubricant for this DME, but we are not able to get the recommended lubricant, because the recommended lubricant is the Lubrizol 509N, which is we approached, but they said we can't provide a little quantity for the research study, and then we used biodiesel as a lubricity and viscosity improver for dimethylether. So we filled the biodiesel in the mixing chamber, and dimethylether is applied from the bottom, and because of the density difference, this DME takes the lubricity improver and then leaves the application tank and then go to the pump. We use the LPG pump because the DME and LPG characteristics are very similar. So we used LPG pump to pressurize the DME, and so that we are able to maintain the line pressure above 6 bar, so that it flows in liquid condition to the high pressure pump of the common rail systems. So then the common rail takes care of the high pressure injection into the system. So this is the schematic of the DME direct injection system. As I told you, and DME improves the global reactivity gradient, and this is the formula we use to calculate the dual fuel Cetane number of the fuel, which is basically a function of the Cetane number of the individual fuels and its molecular fractions. And then based on that, we have arrived what is the dual fuel Cetane number that we have compared with methanol diesel operation and methanol DME. And before supplying DME into the engine, and we done a lot of testing with the methanol diesel, and then only we have implemented methanol DME RCCI studies. We found that, and methanol DME has provided increased Cetane number, dual fuel Cetane number. It ensures that it gives a very high global reactivity gradient, and along with the better characteristics of the DME, so we are able to get a very good reactivity stratifications. Then another problem, as suggested by Professor Avinash, both these fuels, that is the methanol and dimethylether, has got a very low energy content. So because of the lower energy content, and we have to supply more mass of fuel. So to tackle that, what we have done is we have increased the injection pressure of DME compared to the diesel injection pressure, so that we are able to tackle the mass that is required to meet the energy demand of the system, engine systems. This shows and how the LPG converts, LPG pump converts DME into liquid, and the main challenge is arresting all the leaks that comes from every part of the systems. And all the fuel line materials we built with the help of stainless steel, and we made a seamless connection. There is no joints in between to avoid the leaks of DME. And this is the test points that we have performed, and among the 13 test points, for the safety reasons, we have tested only at 8 test points. At low load, we have tested at 4 points. At the medium load, we have tested at 2 points, and similarly at the high load, we have tested at 2 points. So together, around at 8 test points, we performed the experiment with the methanol DME, methanol diesel, and also other dual fuel combinations. This shows the operating conditions of the entire test matrix, and you can see here in this experiment what we have done is we have maintained the energy input constant as well as the CA50 constant, because the AL, they supplied the technical data of the engine, and we know what is the CA50 for each torque and speed, and similarly what is the energy input that is supplied by the diesel, that we maintained constant for methanol dimethylether also, so that we are able to study the performance of methanol and DME under the similar combustion conditions, so that it gives a better, that is, it gives the opportunity to explore the fuel effect of methanol and DME over the combustion process. And this shows the combustion parameters. So we have compared the results of methanol DME with the conventional diesel case and as well as methanol diesel RCCI case, and we can very clearly observe that at all the test points, the dual fuel has started the combustion late, then it's picked up, because we are able to get a longer ignition delay because methanol is resisting the auto ignition, and this high reactivity fuel is injected well in advance. That is the main difference between the conventional dual fueling and the RCCI. Because in conventional dual fuel, normally we supply a high reactivity fuel late than the stock engine, whereas in RCCI case, we normally supply the high reactivity fuel well in advance to provide a longer ignition delay. So longer ignition delay ensures the better mixing. So better mixing ensures better combustion or the quick burning of entire fuel mixture. So we can see that in all the cases, the dual fuel cases started the ignition late, but it has burned very quickly, and you can see that there is an increase in peak pressure compared to the diesel change, and similarly the heat release also. And we can clearly notice that if you compare the heat release rate pattern of RCCI and the CDC, and you can see that in CDC we are able to observe the both pre-mixed and diffusion combustion, which is responsible for NOx and soot production, and whereas in the case of RCCI, you can see that we have only pre-mixed combustion, and it is able to eliminate the NOx and soot because we are having only the pre-mixed combustion. Because normally in LTC, even though LTC handles a diluted lean mixture, because normally diluted lean mixture will have a very low specific heat ratios, but when you combine with the low temperature, low combustion temperature, that results in very high specific heat ratio, so that we are able to get high thermal efficiency. That is the tricky part with the low temperature combustion strategy. Oh, sorry. So these are some of the results at various load points, and you can see that ignition delays is higher for the RCCI case, and also you can see that the combustion duration is shorter for RCCI case compared to the conventional diesel case. And similarly, the indicated mean effective pressures are very high because we have maintained the energy input constant and combustion facing constant. The increase in thermal efficiency is mainly because of the increase in torque obtained for the same energy input. And this is the coefficient of, because we set some constraint to cut off the low reactivity fuel energy ratio. We set 5% as the cutoff for coefficient of variation, and similarly rate of pressure is 10 bar per degree Rankine. So thermal efficiency, we are getting around some 8% improvement in thermal efficiency, and NO and soot is about around 90 to 93% reduction. Interestingly, HC and CO also got reduced in the case of methanol and DI-Methylether because of the improved global reactivity gradient. That is the attractive part. But still it is higher than the conventional diesel case. So even that also we have taken care. The other results. So to take care of the unburned emissions, what we have done is we have combined the multiple injection strategy and fuel reformulation strategy, and then we gone for a mild DOC to reduce the unburned emissions to about 90% in the RCCI engine. So we face some challenges with respect to because DME is a non-polar compound head, and that actually decomposes the sealing materials which is used in the engines. So that is one of the main issues that we have faced. And methanol actually creates the oil dilution that has to be taken care. Since it's LTC, your exhaust energy will be very low, so turbocharger performance will be a problem that has to be taken care. And also, whenever the engine shifts from conventional diesel combustion mode to the dual fuel mode, we observed a jerk. So that has to be smoothened out, and so we developed some algorithms to perform the smooth transition between one mode to the other mode. That also we have developed. These are some publications that comes out from this work, and you can refer and get the outcome of the research. And thank you so much, and I thank the DST and also the Professor Avinash Raghavar, because he was one of the selection panel member for selecting this project, and Professor Avinash and Professor Tipsi from ERI Pune, they recommended this project, and they were able to. Thank you so much.
Sir, I have some question. In what pressure you could pressurize CMA using the LTC?
6 to 7 bar.
Only 6 to 7 bar?
Actually, around 15 bar, we've gone up to 15 bar, so that even though is there any pressure drop in the line, and it will be under 6 to 7 bar, so that There won't be any phase change issues.
So you didn't face vapor lock issues?
No issue. Only in the return side we faced, because injector return normally the temperature of the DME will be very high. So we use the heat exchanger to cool it, and then we pumped it with the help of LPG.
And you were using dual fuel technology. So did you try using 100% DME?
Right. So this project is we committed for a dual fuel. So we have not tried with 100% DME, but there are a lot of literatures are available on 100% DME.
And you said that there were issues with the LPG pump, degradation of the certain components.
Yes, the sealing materials.
So the pump failed?
We failed and we changed it, and there is a separate group, and under this DST project, they were studying about all these issues and what material has to be used for to be recommended for the use of DME. And
you said that you took help from other.
Yeah.
So did they suggest some other pump?
Yes, one professor from Korean Automotive Institute of Science and Technology, and because the Korea, they have developed a separate pump for DME as well as the injector. It is available, I said, but we are not able to get it, and also the industrial partners doesn't allow to go for a different pump, because with minimal modifications, and we want to demonstrate this dual fuel operation, so but it is available.
So you mentioned that there is a higher noise and vibration when you change.
Yeah.
What are the reasons? You also mentioned.
Because it's completely a combustion mode change from conventional diesel mode to the dual fuel combustion. So because
no, but in normal condition, normal condition of dual fuel technology, you didn't observe any.
No issues. We will have it, but that is why we are fixing the constraint.
RCCI is one particular dual mode. It's not classical dual mode. So it's normal. It's like RCCI. So you have a high gradient of pressure. So it's normal. But how do you think that it is it's changed with methanol? Because what is the octane number of methanol?
It's around 110. Close to 110.
Yes, it's 100. So I'm not sure that I can understand what it changed when you use methanol DME.
Engine methanol?
Methanol and DME. What it changed, because you said that there is more noise. So
no, we start the engine with conventional diesel.
Yes.
And then we move on to methanol diesel or methanol DME. That time, during that transition time, there will be a jerk.
Okay.
So, because if it is implemented as a technology, the customer may not like when this changeover happens, this jerk they may not like.
Maybe
sure, but if you have a control unit, you will avoid some operating conditions which generate this gradient.
Yeah, normally we avoid and we go to the conventional mode.
Yes.
So, but we have to come back again during the operation. Suppose if you are jumping to the RCCI mode, that time you have again the same issues. So to smoothen out this, we have conducted a separate study, and
basically noise.
So yes, so in this paper, and if you read, you can get understanding the combustion mode transition. This is last one. This published in Energy Conversion Management.
So it's really how you can manage more smoothly.
Yes,
manage the transition.
because we understood what is the operating condition of the manufacturer when the transition happens. From that operating point to shift to the RCCI, which is the best path. That we have optimally found from the experimental data.
So you also conducted NVH study with that?
We have not conducted the NVH study, but we used to calculate what is the rigging intensity. Basically, that comes from the higher heat release rate phenomenon that occurs at a particular acoustic mode. And we have to calculate that, and that has to be less than 5 megawatt per meter square.
NVH study, we can.
Yeah, we'll do it. We are doing it. And now we are doing the test with the transient ion. So that time when we go for WLTC, and we'll get a lot of problem. So that time maybe we'll do all this.
Thank you.
Okay. So
I have one question. So sir, you mentioned that you have conducted a WHSC point. So my question is that test was conducted using transient dynamometer or
No, it's an engine dynamo.
No, my question is whether it was a transient dynamometer or it was a eddy current dynamometer.
Eddy current dynamo.
Eddy current dynamometer. So sir, how you can ensure that it has conducted a WHSC point? Because
No, we have taken because the air advised us and use that approach and test at the each, because that uses the various operating points. So at the engine dynamometer level, at each test point you can test it and you can get the results. Then it can be matched.
But sir, it can generally in industry it's considered as a steady state.
Yeah.
Steady state test. When you have to conduct any kind of WHSC or any cycle, it should be.
WHSC is a steady state.
Steady state.
It's not a transient.
It is not transient, but when the test conduct, it should be in continuous mode. So my question is whether.
No, it will be in the continuous mode only. It will be in the continuous mode. That is, you can, when the engine is running at one particular torque and speed, again you can change it to the next torque and speed. You can continue it.
And second question is, you mentioned that to improve the liquidity and viscosity, you use the rapid methyl ester.
Yes.
So my question is whether it was onboard mixing or it was earlier the DME filled in.
No, it's onboard mixing.
So how do you ensure the onboard mixing?
This I have shown, we have a separate chamber and which has the DI-Methylether filled at the bottom of the tank, and we separate DME from the bottom of the tank. Because of the density difference, it rises and takes some let's say methyl ester and goes to the LPG pump for pressurized.
And this last question is that have you experienced any kind of drop in nozzle opening pressure during injecting the DME? Because generally what happens when you use DME, sometimes it happens that nozzle hole diameter block.
Yes, we face those problems.
Yeah.
We change the injectors in between also because of these issues. No more questions. Thank you so much.
Mainly about methanol, also DME, but I think there are different things that we can summarize. First, methanol could be an interesting solution for India to participate to the decarbonization of the transportation. And we see two examples of fundamental or application study, but also it's challenging because the fuel has different behavior, different input energy, different lubricity, and so on and so on. So in fact, we are need still to have a study in order to improve, in fact, the use of methanol as fuel for zero carbon solutions.
Long live India and France friendship.